This is a follow-up lecture to complete the section on type 2 error probabilities, section 9.7. And I want to talk a little bit specifically here about power curves and give an example with Excel. So we talked in class about how to find the type 2 error. And we did it for one example. And I just wanted to kind of go over what we did in a more general sense. So you could argue here, right, that we did each of these. So we did have a simple random sample. The normal population, so the data was either from a normal population or it was a large sample, and we had a large sample because this was the one where we were talking about the power to identify a true mean for cars that lasted to 188,000 miles. And we were contemplating a study with a sample of n equals 30. And this is the part that we're just doing for now, just to agree on that. When we went through this, we were over here in this right tail test because basically we had a confidence interval that we built around the mu naught, which is the 185. And so what we're going to do is we're going to come over here and we're going to find this spot, the mu naught, which is actually the right-hand side of the confidence interval. So it's the mu naught plus the z alpha times sigma over the square root of n, and that gives us this value. Now, if you remember, the probability alpha is in the tail in a right tail test, is the probability of a type 1 error. What we're going to do is we're going to say, okay, what happens if this isn't true? And we have actually some actual value over here, some mu sub a. And that's what we're doing here. So we have our mu naught, we add it to get to this point. So this value right here is where this line is. And now we're going to imagine, if you will, that we in some way know that this is the truth. So there is a normal probability around this number. Oops, I didn't do that very well. There is a normal probability around the actual in actuality. Pretend that's symmetric. It's hard to draw with this. Okay, so what we're going to say is that value, that cutoff is the same, but now we are going to not reject, right? So this is the number we were using, and if we had a value on the x sample mean axes that was in this range, we were not going to reject the null. But now we actually are like shifting our whole normal curve over here to the right based on what we want to know what happens if this is the truth. And then this probability under this tail end is what we're going to care about. And so we're going to find that value, and that's going to be the type 2 error. So the type 2 error, the probability of making a type 2 error, is the amount of error in this tail for a given mu sub a, which we may not know really what it is. So we are in this situation for a right tailed. We're going to look for the area to the left of the critical value. So the idea here is we want to find this beta. So going back to the class example, the mean mileage of cars before they die, and by that we mean when they stop working and are not worth fixing. So in class, we discussed that for this example, when we had a normally distributed data where we didn't know the actual length of the number of miles that a car could go, but we were going to assume that it was 8,000 miles was the standard deviation in the population. And at a 5% alpha significance level, we set up this hypothesis. We said, okay, the concern, what we want to know is it possible that the mean is because of synthetic oils was one reason, but is it possible cars are lasting longer than 185,000 miles? So we put our concern in the alternative, and then we put the opposite of that in the null, and we're going to test the bound where mu equals 185. So in order to do this, Nissan is considering conducting a study with n equals 30 cars, and they want to know how much power that study has to reject this 185, if in fact the truth is that it's greater than 185. Okay, so what we want to see in order to answer that question, to figure out the power, is we're going to kind of go backwards here. We're going to say, okay, well, the power is 1 minus beta. So we talked about that already in class. And beta is just the probability of a type 2 error, which I just went over. And we went over that we can only calculate this for specific values of truth. So in the last example I just showed you and reminded you of, we were assuming it was, well, we went over it with 188,000 miles in class. And I'll go over that now in a second. In order to determine the power, we also need the X bar alpha. This is the sample mean critical value, which we get from solving for the X bar alpha in the z-score that we got for the test statistic. Actually, no, this is not from the test statistic. This is the z alpha that corresponds to our alpha in this case in this example was 5%. So we calculate this backwards, remembering that this, the standard deviation of the sample mean is the standard error. And that for this example of 8, where we assumed an 8 in or that we knew sigma, divided by the sample size of 30 gives us 1.46. And so calculating all this back, the sample mean critical value is 187.4. And so what that means is that since this is a right-tailed hypothesis, beta is the area under the normal curve that is centered at the potential true value. If this is the truth, we want to know the area to the left of the 187.4. Now remember, this boundary actually is coming from the null. And if we can build that confidence interval around the null, so it's symmetric on either side, we have the mu naught plus z alpha sigma times sigma divided by the square root of n, and mu naught minus z alpha times sigma over the square root of n. So this distance in here, this is a 95% confidence interval. And what we are actually, if you recall, is we're trying to find out what's the probability of, this is a type 2 error, that we are going to have some value in here when the truth is outside of that confidence interval. Okay. So in our class example, if the true mean was 188,000 miles, we determined that beta was 0.34. And the way we did this is we put in, to the Excel function norm distribution, we just put in the value that we were cared about, that 187.4. This is where we put in the mean that we are checking. What happens if this is the truth? The 1.46 we are assuming we know right now, and we always put true in this function to give us the cumulative distribution all the way up to the number on the area under the curve up to the value 187.4 from the left. And when we put this in, we get that it's 0.34. And that the power then is 1 minus the beta, or 0.66, or around 66% power to reject H naught if the truth, so we should say if, right? So we have 66 power and it depends on this value being the truth, right? So what if it's actually bigger? What if it's 190? What's beta? Well, everything's the same in our normal distribution function, except the truth. We change out the 188 and now we put a 190. And when we do that, we get that the probability to the left of that 187.4 is just 0.0375. And this is not surprising. As the truth is further from 185, so here 190 being the truth, and basically our null hypothesis is becoming increasingly wrong. So at 190, we have smaller probability of not rejecting H naught. In other words, there's smaller probability of making a type 2 error. So the power for this possible true population mean mu is 1 minus beta, or 1 minus 0.037 or 0.9625, or now we're at 96.25% probability of rejecting 185 if the truth is at 190. So we're gonna now get into the topic of power curves, because in reality, we never know the true value of mu. So in practice, what we do is we calculate the power based on various possible values of mu sub a. And then we graph them as the power curve. So for a given significance, we leave the alpha the same, and we leave the sample size n the same. What changes is the mu sub a, for which we calculate the power. And then we graph for different values of mu sub a, we graph the power on the y-axis. And I'm going to do an example of that here in a second. But what we really want is for alpha and beta to both be small. So the only way to do this is to increase the sample size n. And this is because if you go back and look at all the calculations that we did, when we were increasing n, what happened was, since the sample mean has a sampling distribution with a standard deviation given by sigma over the square root of n, as n gets bigger, that denominator is getting bigger and that standard error is decreasing smaller. And so therefore, we're able to decrease both alpha and beta by having the sample size go up. And as the sample size n goes up, that increases, beta then goes down, and then the power increases. Okay, so now we are going to go through and actually look at not only building a power curve, but also just doing a whole analysis from the beginning to end of what I would say soup to nuts here. So for the hypothesis test using a one mean t-test, and now I'm not going to assume I know the sigma. I want to go through an example where I'm going to estimate it from the data. So again, we've just talked about this. X is the number of miles in thousands of miles that a car has before they are no longer operable or fixable. And mu is the population mean number of miles in thousands of X, of how long cars last. We're going to do this hypothesis test with a significance level alpha of 0.05. And setting up the hypothesis test with the null and the alternative, as we've already done in class, we are going to be we see that this is, because mu is greater than the number, it's a right-tailed test. All right, so now we're going to assume that Nissan was okay with a sample size of 30. And we're going to get some sample data. So here's some sample data. So the first thing we're going to want to do is our preliminary analysis. So we see here that we have, it looks like 24 data points, but let's go ahead and get some descriptive statistics on this data. So we're going to go up to data and come over to data analysis and come up to descriptive statistics. And here we're going to give the input range, and I'm just going to select this column of data in here. I'm going to say, yes, there's a label. And I'm going to pick the output range to be basically, whoops, I got to click inside that, and then over here. And then I want to have summary statistics provided. So I'll say okay to this. And here we have that mean is 181.75 in this data. And the count is 24. Okay, so now we want to know, before we go on, since the sample is less than 30, we're going to need to check if it's normally distributed and if there's any outliers. Now in Excel, I can get a quick read on whether or not there's an outlier by using a box plot. So I'm just going to select that data again, and I'm going to come over and go to the middle here, what looks like a histogram, and the second choice down is a box and whisker plot. And we can see here that we do indeed see what appears to be an outlier. So this we can just say is a box plot of sample data. But I just did that because it's really quick and easy to do it, and I wanted to remind you how to do it. But really what we need to do is a normal probability plot. So what we're going to need to do is since n equals 24 is less than 30, we need to check if the data is normally distributed with a QQ. Okay, so the first thing we're going to need to do is get the observation number. So let's say that we're going to need 1, 2, 3. We're going to put this through. And I can just drag this down until I have 24 listed here. Or I believe I can just go into this fill, series, columns, linear, step value 1, stop value is going to be 24. I think I can say do it this way. Oh, I didn't like that. Let me just drag this down then. I think the reason I didn't like that is because I had 1, 2, and 3 already typed. Okay, so now I have the observation numbers. I'm going to center them just to make life a little easier for me. Okay, and this data, oh boy, I don't want to center that one. Let's just leave it over here. Okay, then after I have the observation numbers, I need each of the observations rank. So that is from, if I were to order them from smallest to biggest, what would be their rank? And I can just get this without having to sort. I can just say rank average. And I'm going to get this number right here. And I want to refer to this whole set of numbers. That's our data set. And the order I'm going to go in is ascending. So I hit that. So I see that the value 181 is the 6th from lowest to highest, smallest, if you will, value. Now I want to copy this formula, but I don't want this part right here to change. So I'm going to highlight it and hit Function F4. So that's frozen, and that's an absolute reference to those cells. So it's not going to change. Those cells won't change when I copy this formula down, because I'm going to select that cell now, and I'm going to double click on this little green arrow. So now I have everybody's rank, every one of these numbers from our sample data set, their rank. Now, what I want to do next is I'm going to get the percentile if this was normally distributed data, and I'm going to do that by just getting a continuity, sorry, I need a parentheses there. I'm going to take that number and I'm going to subtract 0.5, that's the continuity correction. And then I'm going to divide by the number of observations, or the count. Okay. So we're going to just get if the data was distributed normally, what percentile of the data does this represent right now? Well, right now we're just getting the percentile. So I want to copy this down. I don't want this bottom number to change, so let me freeze that one. Oops, I selected the division symbol too. I just have to click somewhere in the number anywhere. There we go. I mean, in the cell reference. Okay, now that I have that, I can copy this down. And I now have the percentiles based on the rank of all the data. And from this, I can get now the theoretical z-score. if these numbers actually came from a normal distribution. So to get that, I'm just going to say, I'm going to assume the percentiles is the probability from a normal distribution. So I'm going to say norm dot S dot inverse. And I'm going to select this probability right here. And then I'm going to repeat that by double clicking on this lower right green little square. So now I have all the theoretical z-scores. I'm going to compare those with observed z-scores. And the observed z-score I'm going to get by getting the actual z-score calculation here. So I'm going to say this is going to equal the number itself. So I'll start with the first one. Oh, once again, I'm going to need parentheses. So let's go equals parentheses. That number minus the mean. And that whole thing is going to be divided by the standard deviation, which is right here. So now I have this value right here. So that's the observed z-score. So now I want to copy it down. So I'm going to come in here and I'm going to set the reference to the mean and the standard deviation to be absolute references. So let me come in and calculate those for all these values. Okay, now I want to compare these two. I want to see if they land on a line. I expect them to land on a line. So I'm going to select all these numbers and I'm going to go over here to insert and come down to the scatter plot, and I'll pick the first scatter plot and I'll put them right over here. And I can see that there is what appears to be a problem here because this value is not on the line. The rest of them might be sort of on a line, but this value is really making it hard to see. And that's probably the same value that was here. So I do see that it appears like it's a normal distribution, but before I can say that for sure, I need to get rid of this outlier. So I need to find out where this outlier is. And I can do that. When I look at my data, I can say, okay, what value has a observed z-score that is like minus, 4 something, and here that number is, it's the observation number 18. Okay, so what we could do is we could just come over here and insert another row and then just copy this numbers down so we can know which one we're talking about. So the 18th one is this 49. We probably could have eyeballed that as well. And clear those drawings. So that's the number we want to remove. So what we're going to do is we're going to basically create some more data and run this all over again. So we'll just say this is outlier removed. I'm just going to copy this over. Okay, and I'm going to come down here and I'm going to remove this data. So I'm going to right click and hit delete. It's going to ask me what to do. I'm going to say shift cells up because I basically want that one removed. Okay, and now I need to do everything we just got done doing. So I am going to pause and let you do that. So this is the descriptive statistics. Now that the outlier is removed, we see that the box plot now looks clean. And if I do the normal probability QQ plot, I'm seeing that all my data is pretty close to landing on a line. So the data does appear normal. And that outlier, I'm going to pretend that we did some inquiry and we found out that that car was in an accident. So we realized like, wow, we really can't, we have to change the population here, and we're justified in doing that because that's going to throw off the answer that we were asked to investigate. So we're going to change the population to cars that do not have any accidents. Okay, so let's go back over herd hypothesis test, and we're going to change what the population is. So this is the population of cars without accidents. We definitely would want to get buy-in from our management or our team if we did something like this to make sure that it was clear that's what we were doing. Okay, so after the preliminary analysis, n is equal to 23 because we removed one. So that means that the degrees of freedom are going to equal the 23 minus 1, or 22. Now we're going to come in here and we're going to say, okay, well, what's our sample mean? And we're going to point that to our sample, our outlier removed data, and get that sample mean. Oh, sorry, I forgot to hit equals, didn't I? Equals. And now I point to the cell. There we go. And then we are going to have the standard error for our sample data. So that's going to equal the sample standard deviation. So we'll go over here, we'll get the sample standard deviation. It's actually already calculated for us right here. 1.689, so we can just point there, and that's a standard error. And then what we're going to need to do is get the t-test, the test statistic. Okay. And so for that, what we're going to do is we're going to say, well, that's going to equal our sample mean minus the 185 that we believe that we're testing as the null hypothesis. And we're going to divide that by the standard error, which is right here. Okay, so now that we have the test statistics, we're going to do the p-value, which, if you remember, is going to be the area. So it's always a good idea to do a little sketch of what we're trying to do here. Let's say we draw a normal curve, and this is going to be a t-distribution now, but it's very similar to the standard normal in that it's symmetric about 0. And we're going to take this number right here, the 1.49, and we're going to graph it on here. Okay, so let's say that 1.49 hits there. Then our p-value is just the area under the curve, because this is a right-tailed test. It's going to be the area under the curve to the right of this number. So we want to know what this area is in here. And that's what we're going to do to get the p-value. So to get that p-value, we're going to come in and we're going to say, okay, because it's to the right, and Excel always gives me the area under the curve that's to the left, I got to say 1 minus. And this is going to be the t distribution. There is an option for right tail. So if you do this a lot, that might be the one you want. Since we're learning, it's probably better not to confuse yourself too much with too many functions. But we're going to put in this amount, the t statistic, and then we're going to want to get the degrees of freedom. So we'll click over here on where the degrees of freedom is, and then we're going to choose true. Oops, what happened? There we go. So now we see that we have, I'm going to erase a little bit of this because it's a little bit in my way. Okay, so we see that we have a 0.0748 amount of probability out here in the tail. So what we're going to want to do is determine, we want to compare. So we're going to run the test. We're going to compare the p-value to alpha. So we're going to want to know is p-value less than or equal to alpha. So if we look at this, it is not, right? 0.07 is greater than alpha. So one way you can do this, by the way, is you can just say equals, and then you can run the test directly. You could say p-value less than or equal to alpha, and it's going to tell you if that's true or false. It's false, so we do not reject the null hypothesis. And so the interpretation of that is that there is not sufficient evidence to reject that cars last, on average, 185,000 miles. Right, so we have a meeting and we tell management what we found, and then so they have a follow-up question. Like, how much power did this study have to detect a difference of 186,000 miles to 205,000 miles? And then also, if another study is conducted with n equals 10, how much power does it have to detect a true mean of 195,000 miles? So in this hypothetical example that we're coming up with, maybe the management has figured out that at 195,000 miles, it has to close down a factory, which is 10,000 miles more than the cars were lasting in 2010, which is where that 185,000 mile number came from. Okay, so in order to do this, we're going to look into answering the question about power. And what we're going to do is we're going to come up with power. We're going to do a power curve here. And they asked us to look at true values. So this would be the, I'm not sure if I can do it here, but let me try. It's going to be the mu sub A. Okay, so this is the actual value. So we'll just put that in here. We'll say the actual mu, population mean. So, and let's say we want to start at 186. And let me see if this fill thing now works. So we got the 186 and we want to go, we want to do a series. We're going to step by one and we're going to stop at 205. Okay, let's just say, and we're going to put it in a column. Okay, so now we have those actual values. For each one of these, we're going to want to get a beta. So beta, which is the probability of a type 2 error. Let's make this a little wider. Okay, so what this is going to be is basically what we did for what we're going to need to do is obtain the critical value the way we did in class. So the first thing we're going to do is we're going to answer the question about the power that this test had for that range of values. So we're going to set the alpha equal to 0.05. And we're going to set that sample size at the 23. Okay. And what we're going to need to do is get the T alpha associated with that, with this amount. So the T, and maybe we can call this the T score associated with this. And maybe I'll just make this column a little bigger so we can handle this over here. Okay. And so it's going to be, since this is a right-tailed test, it's going to be, well, we're just going to get the T-score associated with 95% probability and a degrees of freedom of 23 minus 1 or 22. So this is going to be the T distribution, and actually, sorry, T inverse, because we want to actually get the T value, the quantile. So we're going to put in the probability of 1 minus the 0.05, and then degrees of freedom is a 23 minus 1. Right, so we get that it's a 1.717. And the standard error we already knew from from our outlier data here. We have our standard error. And so let's just pull that over here as well. Actually, I'm thinking that all this needs to be moved down. Let me just move this. Okay. So let's get our standard error. And that's going to equal the standard error in that data. And finally, from this, we're going to get the sample mean critical value. So get that over here. So it's the mu naught that's coming from the null hypothesis. And then we're going to take this T alpha and comma degrees of freedom. We're going to multiply it by the standard error. All right, so this is going to equal the 185 plus, and again, this is the right-hand side of the 95% confidence interval. So it's going to be this number times the standard error, or this number right here. Okay, oops. And now we see that it's 187.9005. Okay, so what we want to know is if this is our critical value, what's the probability to the left of this? Because this is a right-tailed test, we're going to do the probability to the left. Okay, since we're going to do this with a T distribution, what we're going to need to do, and Excel doesn't allow us to automatically choose our associated mean, we're going to actually need to get the beta by getting the T-score shifted using the actual mu. So to do that, we're going to add another column here. So let's just go ahead and insert a column. And we're going to call this the T value for the alpha. Basically, this is going to be the one associated with the sample mean critical value, the X bar alpha. If we assume that the true actual mean is this value right here, and let me just write that as actual mean. I think it might be a little bit easier. Just a little easier to read. Okay, so the T value, if this is the actual mean, then the T value that we're going to get for the X bar critical value that's associated with this, right, is going to equal parentheses, the t-value, which is the number right over here, the x bar critical value, minus the distance from the actual mean, okay? And we're going to divide that by the standard error. Okay, so we have this value right here. Now this one we're going to copy down, and what's going to change is the actual real true mean that we're going to get this t-score for. But what we don't want to change is the position of the x bar critical that we're going to be converting. So we're going to go up in here and we're going to change the blue to a absolute reference instead of a relative reference, and we're going to divide by the same standard error in all of these that we're assuming, that we're estimating, excuse me, using our sample data. All right, and it's based on that standard error is also, recall, is based on the sample size of 23. So now that we have all this data, we're going to go ahead and get these values. And then what we're going to do for each one of these, remember this is based on, so I'll say t-value associated with x bar, x bar equal to this 187.9. And so here we're going to say, okay, well, this is going to be the probability to the left. So all we need is the t distribution value for this t-score, and the degrees of freedom are going to be the sample size minus 1. Oops, and I forgot to say cumulative, didn't I? True. Oh, now we're going to copy that formula down, but what we don't want is the sample size to change. So we're going to make that an absolute reference. So function of 4 puts the dollar signs in front for me, or you can hand type them in. So now I'm going to have all this beta here, these beta probabilities of a type 2 error, depending on if the actual mean, so as the actual mean gets further away from this 185 hypothesized mean, this number right here is getting further away from this potentially true mean. So we get, it's a smaller and smaller amount of area to the left of this t-score. Okay, so now that we have this, let's go ahead and get the power for this. So this was one step different than what the book has for using the z-score, but this is more realistic. So the power, it was going to equal 1 minus the beta. So we'll just put this in here. And this one we're going to copy down directly. There's nothing that has to be fixed. And now we're going to get a power curve for this. So what we want to do, so we have, these are the values that we want on the y-axis, and these are the numbers we want on the x-axis. So for every possible true mean, we're going to put this together. So let's go ahead and select this. So I select the x-axis, and now I'm going to hit the control key, and I'm going to select the y-axis values, or the power. Now, I let go of that, and so now they're both selected, and I'm going to go to insert, and in insert I'm going to select, sorry, not the line chart, oops, under this chart I want to select the one that connects them. So it's going to look like this. Okay, so I see that I get the power automatically put as the title, and that's fine. I can do that. I can leave it that way, and then I can add a axis title to the primary horizontal axis, and I can just say here, the true mean of how long cars last. And I can say, maybe we should say in 2022, in thousands. It's always good to have your units when you define your axes of miles. We'll know what we're talking about here. Okay. And it might not hurt to make this a little bit bigger. And let's go over here and look at this. So what we're saying is if the true mean, let's say that they have a production cutoff of at 190. If the average is 190 or above, then they would maybe close down a factory, for example. Maybe they could say that. So they want to see how much power this sample size of 23 had to detect to reject 185 from a sample if the truth was that it was 190. So the power here we see is by hovering over the point, you can see the y coordinate, and it's 0.8865. So almost 90% power. I believe, come over here and click on this axis and format this. Oops, wait, I wanted to get the axis. How do we do that? There we go, format axes. And let's go ahead and say that we want the units to be 0.1. Okay, that just gives us a little bit more granularity, spreads that out so we can see that it is pretty close to 0.9 when we reach 190. And at 195, if the true mean number of miles cars last is around 195,000 miles, this study with an N of 23 and an alpha of 0.5 has like 100% power. So it's saying that if that's what the mean would be, you would definitely reject the null. You have 100% power that you would not keep the null. And this is saying that if the truth was out here at 190, the current study, so remember, let's go back and remind ourselves, we did not reject the null. We said there was not enough data to claim that the 185 was not right, that, what it could be 185 still. And so we're like, so how much power did it actually have at 187 to detect that? So let's go over here. So like around 187, yeah, so that's where that 66% power came in. Okay, so you can see that there. So this is the, as the sample size goes up, this power curve is going to go up more steep. So maybe we can explore that in the opposite direction. We're going to look at what happens if the sample size goes down, because usually these kind of studies can be very expensive. And so maybe they want to run another second study, and they're just wanting to know if they run another small study, what kind of power it would have. So let's rename this power curve. So to do that, everything would be the same. So in here, we would just say, suppose we went with n equals 10. Then we would have a different, our alpha would be the same, but our t-score would be different. Okay, so t-score with x bar alpha would equal here. So that would be t inverse. And the probability that we want is 1 minus 0.05 or 0.95. So we could just go like that. And the degrees of freedom that we want is going to now be the sample size minus 1. So same formulas, it's just that now we point to the 10 instead of to the 23. Okay, and the standard error that we're going to get is going to be the standard deviation. So this, now we need to calculate it because we are changing the sample size. So we're going to assume that same sample standard deviation. So the standard error and this is going to equal the sample standard deviation. So we'll go get that value and we're going to divide that number now. And it's not going to be provided to us because we are actually going to divide by the square root of n. And n here is 10. So we'll put that here. All right. So now we see we have a standard error of 2.561. And then the X bar critical value that's associated with this. Let me just copy this over. Maybe just a little bit to the left. Okay. And that number is going to equal, so now it is still the 185, which is our mu naught, plus this alpha times this standard error. So this is our new value of our X bar critical. So when we're going to calculate for those same means, we're going to calculate these values. And I'm just going to copy the first row because we're going to need to modify it. So let's just put that over here. So the t value associated with the X bar of 180. So this one's going to be now not X bar 187.9, but 189.7. And I'm just getting that from what we just got done calculating right here. So this is associated with this 189.7. And we're going to take this number that's not here. We want the red box to be this number, the 186. We want our X bar critical value, this one, to now be, so I'm just dragging the boxes over. This is a great way in Excel to modify equations. And the standard error is going to be this one right here. Okay, so now that we've done all those things, we can hit enter. Let's click back on it and make sure we got the right thing here. All right, so we are going to say this is our sample mean critical value. If the true mean is 186, we're going to subtract those two. That makes sense. And then we're dividing by the standard error that we calculated for a sample size of 10. That looks good. Now we're going to get the probability of that. And again, the probability is going to be that the probability associated with a t distribution with a sample size now of 10 minus 1. So we have to modify that. And then the power is going to be 1 minus the beta, which is fine. So now that we have all this, then we can copy this down. I think to here, we have it lined up correctly. There we go. Okay, so now we can add this power to this curve. And let's say, I'm going to say here, this is the n equals 10 power. Okay. So let's go ahead and just do this by deleting this. I'm going to do both power curves at once. So again, I want this as my x-axis. I'm going to hit the control button and select this one. And then I'm going to select this one, which is my second power here. Let's see if we're able to get this Excel to give us what we want. So it was able to do it. So power and n equals 10 power. So maybe here we need to modify this to say n equals 23 power. I thought that would automatically update. Oh, it did. Good. Okay. So you can see that we have less power for the same truth, the true mean with n equals 10, we have far less power. And let's see if we can make this whole graph bigger and change the x-axis like we did a second ago. I'm sorry, the y-axis. All right, so we are able to see that now, if the truth is that cars are lasting 190,000 miles on average, a study with 10 will only have a 55% power to reject the null and identify that that null was not true. So there's a good chance we would not reject the null with only 10 cars. But if our cutoff is 195, so this is how this can be used to make a decision. If your cutoff is 195,000 miles before you would maybe close a factory, you could say, why do we need to run this $1 million study with 30 cars when we can run, a third the cost, and with n equals 10, we still have 90, around approximately 97% power to detect that, to detect and reject the null. So this is where you would say maybe a sample size of 10 is sufficient, if depending on where your cutoff is, where you're going to be making a decision. Okay, and this is why I wanted to cover power, because it's an important aspect of decision making when you decide sample sizes, and the sample size is what drives the power. Sorry, that drives the cost.